we go on the overview of the Marvel project, but from a technical and scientific point of view. I'll thank Dragana Bajovic, which is Associate Professor at the Department of Power, Electronics and Computer Engineering of the Faculty of Technical Science at University of Novi Sad, for helping us in this task. Please, the floor is yours.
Okay, thank you, Beta. So let me pick up first the pillars of the architecture. Let me pick up on the pillars to show some examples of what exactly we will be doing in each of these pillars. So yes, so they're real heterogeneous distributed big data in smart cities. You will hear more about that in the pilot presentation. So I will focus here on the multimodal analytics and also edge fog to cloud continuum computing. About multimodal perception intelligence. So of course, it's intuitive and it's clear that the more the data that we have, the more the data sources, audio, video, IoT sensors, the more modalities there are. It's clear that we can expect better accuracy, more insights, more valuable knowledge. But what in particular, what are the rationale behind this? Are there any specific events, some specific ideas how exactly one modality can help the other or complement the other? So, for example, if we are talking about visual, let's say, anomaly detection, if there are some unfavorable environmental conditions like low visibility, then we can perhaps use the audio modality to detect some event, like detect a vehicle in the pedestrian area, or perhaps if in one modality we cannot detect some event like people screaming or a gunshot, that's also a clear example. There can be also modality dropout or some occlusion, in which case we can benefit from the other modality. So there is certainly this robustness idea and also increased accuracy, of course. Another specific thing that we will be doing and where research is kind of at early stages and we are very excited to contribute is let's try to use these modalities in a synchronous way. Let's try to kind of mimic human perception to fuse them early enough to achieve very fast and very accurate insights. Some state-of-the-art and also very novel technologies in audio analytics that are kind of within our pillars are automated audio captioning, where just from a very raw audio signal, you pass it through this complex system and you get a contextual description of what's going on in the environment in like a human language form. So you can see here we have this audio signal on the left, and the output of the system is describes you completely what's happening in some city square or in traffic and so on. Another example is to localize events both in time, possibly overlapping events, and also detect where exactly in time it occurs and where exactly in place it occurs. The second pillar, which is complementary to the previous one, is about how best we can exploit all these vast amount of very distributed computing resources which already exist in any smart city infrastructure. Possibly there will be others, there will be legacy infrastructure, and then you can add more and more to it. Specifically, there is this huge push to go with computations at the edge. So how exactly we can achieve faster, better analytics, more responsible AI, more efficient AI? So here on the figure you can see this large octopus-like platform, which kind of stretches the tentacles in all the three architectural tiers, so cloud, fog, and edge. And in the cloud, it goes from the HPC or cloud infrastructure to small data centers in the fog tier, all the way down to these small devices, to cameras, to Raspberry Pis, perhaps some stronger edge devices like edge GPUs. So basically, it can go to anywhere where any small software piece can be run, installed, and run. So why do we want to achieve all this complex deployment? Because we want to be able to kind of like in real time or in continuous way to monitor the deployment, to monitor the performance of these services, to possibly do redeployment over time, and achieve, of course, the more efficient way of computations. One specific thing is edge processing, and here we are aiming at embedded AI. So push AI and this inference early enough close to the sources to get faster insights, very fast time to reaction, also to get privacy protection, because the earlier you protect the data and anonymize the data, this is better with respect to some regulations like GDPR. And finally, we do this in a very responsible way because we protect and preserve bandwidth. If we do inference early enough, we don't need to transmit all this heavy audiovisual data. We can just transmit some very small pieces of information like inference results and pass on to the other services for visualization, decision making, and so on. Okay, so let me now tell you a little bit more about this system view that Sotiris was showing, the Marvel architecture. So we have in total 29 technological components of a very wide range of functionalities and their associated framework roles. These components have been grouped into 7 functional subsystems that we will now be looking at in this Marvel architecture figure. So as you can see, it's a very complex figure, but each, first of all, there is color coding, which helps, you know, to understand the different roles and how they're grouped together. So let me start by system, just to get a complete view, and then we will delve in, zoom in into each of the subsystems to see what are the particular technologies that we will be working with and developing. So first we start, of course, with the data. The data originates from cameras, from microphones, from drones, from smartphones. And we have this yellow sensing and perception subsystem, which creates this data. But in this subsystem, we are taking not only the data sources and enabling hardware and software for data capturing and transfer, but also some examples of early AI. So as mentioned before, we want to try to push AI as down as possible, as early as possible, meaning in terms of the where the data is produced. And we have some components like sound event detection at the edge, or cat flow for monitoring traffic, and similar. After the data is being produced, it's passed on to this red subsystem, which has 2 roles. One is to anonymize the data and kind of like prepare it for further processing in that sense, but also to protect the data from tapping into it, from changing the data. And so we have a number of components to achieve that. After the data is being sanitized, then it's passed on to this blue subsystem, which is the named data management and distribution subsystem, which can, since the data is anonymized, it can freely, you know, move the data, place it where best utilized by the application according to the user needs. Specifically, one specific goal of data management is to pass the data to this pink subsystem, which is the core AI subsystem of our project. It's audio, visual, and multimodal AI subsystem, and this subsystem has the role of course, build all these machine learning and deep learning models tuned for various tasks. I'll talk about specific tasks in a moment. We've already seen some examples like audio-visual anomaly detection, sound event detection, localization, automated audio captioning, and similar. After the models have been produced, based on, you know, all these large amounts of data that's being collected by these heterogeneous data sources, models are passed on to this violet subsystem, which kind of post-processes them in several ways. One is, first, we want to compress the models, because many of the models as is, they cannot be they cannot fit into edge devices that are available. So we have a number of technologies for compressing the models, but also technologies for tuning further the models via federated learning with multiple parties that participate in training process. And finally, we have this platform, which is the Octopus-like platform, Marv-Dash, that orchestrates the whole deployment and optimizes deployment in a continuous manner. The whole thing runs on the infrastructure which is available at our pilot sites. They feature cloud and fog and edge tiers. And finally, to complete the pipeline, we have this green system, the user interactions, the user interface, decision-making toolkit with some advanced visualizations for real-time decisions, but also for long-term business decisions. And last but not least, the data corpus that we will talk about a little bit in more detail shortly. Okay, so just a little bit more and zoom in view in all of these subsystems. So first, in this yellow subsystem, we have, as mentioned before, the sensing elements, the devices in the edge tier, and including some embedded AI. So for embedded AI, what we have is currently is sound event detection at the edge, which is a small neural network that can fit very small devices like microcontrollers, for example, and it can enable to directly in situ detect some environmental events, audio events like, is it a car, is it a bus, is it a dog barking, and other events of that type. We also have advanced MEMS microphones. We have two different hardware and software configurations for real-time data streaming from the edge devices up to the cloud. Now we have this red subsystem, which, as I mentioned, has a dual role. First, there is the EdgeSec component, which spans all the three tiers and enables to protect the data that's flowing end-to-end from the devices to the cloud from tapping into, from altering the data, but also not only the data, but also to protect the code that each device is and each installed piece of software in all the devices along this edge for cloud continuum. The second role of this subsystem is to achieve anonymization to ensure privacy and protection of personal data. Now, with regards to anonymization, I would like to make a couple of remarks here. So we will have both video and audio modalities, so we are going to anonymize both of these modalities. But in contrast with what's currently done in the industry and in practice, meaning, okay, you detect, for example, a person's face and then you blur it. Here we want to go beyond that and do something more exciting in terms of research and also something more usable for smart cities. So we will be doing specifically techniques like face swapping, where you use another person's face to protect the privacy of the original person, but then you also preserve some contextual information like is the person smiling, or is it in some anxiety, under some stress, or is there maybe some event that can be indicated by this emotion detected on a person's face. So there are currently a number of technologies that do that, but they're very, very early stages, so it's very challenging to make them work in this real-life environment. So there will be a lot of interesting work there. Another challenge is how to push these complex models, complex deep learning models to the edge to achieve GDPR and privacy by design. So so these are the main innovations and the main challenges in this subsystem. Now, the subsystem deals with, as I mentioned before, with all these large amounts of data from all these data sources and different levels of the architecture. Here we have 4 different management platforms. 3 of them are dealing with data management and processing on the fly, augmenting the data possibly during processing the data streams. They're based on technology like Kafka or NiFi. They're complementary. They can talk to each other. They have common interfaces. And we also have the fourth platform, which is conceptually different and achieves, it's in line with this optimized deployment, optimized management of data. So what we want to do there is to try to distribute the data the best way possible to achieve optimized processing of data. So where the AI task needs the data can be shifted there and pushed there in the optimal way, accounting for wireless connectivity, for cost of data transmission, and similar. Now, the fourth subsystem is the audiovisual and multimodal AI subsystem. Here we have a number of different components, as you can see from the slide. There are audio-based components, there are video-based components, but there are also these multimodal audiovisual components for tasks such as audiovisual anomaly detection. If there's a pedestrian somewhere where the cars are, the system should detect this immediately and perhaps try to help this person, or just inform someone who is responsible to take any actions. And also we have audiovisual crowd counting to analyze the crowds that are in some city square. We have audio analysis like acoustic scene classification, automated audio captioning to understand what's happening in the environment, sound event localization detection. One specific task that we might be, that we will be working towards is to combine according to our pillars, to combine different modalities to achieve very efficient and very fast time to insight, efficient perception. For example, Giacomo was talking about hundreds of cameras, and it's very difficult for one person to process. Of course, it's impossible to process the information from all these cameras. But if we can somehow detect, use, let's say, the audio modality and sound event localization detection to detect some anomalous event in a specific square and put, let's say, a bounding box around this event, then this specific data stream can be selected from the data management distribution system and projected onto the user interface, so that, say, a police officer or some city authority does not have to, do random guessing what is the most important camera to look at, but the system will do it automatically for him. The fifth subsystem is optimized dash-to-facto cloud processing and deployment. There are two things here. One is we want to first kind of post-process all the models and try to make them better, try to make them fit the edge, try to optimize them using federated learning with various different sites. For example, for audiovisual crowd counting, we have crowded squares in Malta, in Trento, in Novi Sad. And all these data have some specific data distribution, some their specific properties, but there are also some generalities and commonalities that we can explore to build some nice global model that is better than the models produced by individually processing data at each of these sites. If we are talking about, but there is privacy, of course, we cannot share this data. Well, this technology does not have to, allows you practically not to share the data and still get the best accuracy possible by just communicating certain functions of the data, not the data itself. So there is this flavor of optimizing this model that we were obtained from the AI subsystem, but also there is the second thing is, of course, we have to, once we get the models, we want to deploy them where best served by the applications. And we also want to redesign possibly deployment based on operating conditions, based on environmental conditions. For example, if we detect there is low visibility, let's turn off video modality, let's put more emphasis on the audio modality. And of course, this has to be done in a continuous manner, improving constantly and constantly monitoring the performance of the whole service. This is done by the Marv-Dash platform. That's, again, this octopus-like platform, which has points of presence and at all computing points and can orchestrate the whole process of computations. Of course, this all has to run somewhere at some devices, and we have, as mentioned several times, we have this continuum edge fog cloud infrastructure with specific devices at each architectural tier. Now, the exact infrastructure depend, of course, on the pilots, and there are several heterogeneities there. So some pilots, for example, have Raspberry Pis in the edge. Some other pilots have Intel NUC in the edge. So depending on this heterogeneity, we are going to tune specifically to each pilot infrastructure the whole instance of the Marvel architecture. And finally, the system outputs the decision-making toolkit and Marvel Data Corpus as a service. So this is the user interface of our platform. So there are two things here. First, we have the decision-making toolkit, which embeds some advanced visualizations in there, which are tailored according to specific use case needs. So we have already been working a lot on that, and you will hear more in the MVP slot with specific figures and some nice examples of user interface. But let me now tell you a little bit more about the Marvel Data Corpus, because this is also kind of within pillars of the project, and some what we feel is an important output also from the project. So Marvel Data Corpus will be, and we are working towards this, building and augmenting this data each day. As Sotiri said, it's 24/7, the data is constantly arriving from the cameras and microphones. So it's going to be a very large collection of audiovisual data, properly anonymized. And also, at some point of the project, it will be also open and publicly available to all interested parties that want to play with this data. For example, researchers that are interested in building their audiovisual models, smart city authorities to gain possibly some insight for their own smart cities. And also one specific feature of the Marvel platform and Marvel Data Corpus is that it will support advanced queries with data filtering, possibly based on some events that you're in particular interested in, and so that you can search based on your interests. So this querying will allow you to do that. And that will be all from my side. Thank you so much.